Welcome to another video. Here I'm continuing the integrals in section 7.5 of the Stewart Calculus Early Transcendental 7th edition textbook. Okay, we're just practicing a lot of integrals to get our techniques down and be able to kind of think through how to approach different types of problems. Some are more easy, so hopefully the decision is much easier once you get a lot of practice. Some are more obscure, so you may have to try a few things. Okay, so we left off on number 12. We have this integral x over x to the fourth plus x squared plus 1 dx. So how can we solve this? I mean, the bottom is not factorable, at least to me. I don't see it right away. So it won't be partial fraction decomposition, probably, so we can rule that technique out. How about trig sub? Is not something squared plus something squared, so probably not that. We can't really make it, actually we might be able to make it into that if we somehow makes this to a quadratic. Okay, it's clearly it's not trig integral. Integration by parts, I kind of don't want to do that because if either our u or dv is 1 over x to the fourth plus x squared plus 1, that's hard to integrate. So probably not by parts, at least from here. How about just a normal substitution? Well, if I let u be x to the fourth plus x squared plus 1, du would be 4x cubed plus 2x dx, which is not like the top at all. So I'm out of ideas, am I? Or what else can we do? So hopefully you can see that x to the fourth is just x squared squared. So let me write that. So let's write it like this. Now what if we make a substitution? U is x squared. Du would be 2x dx. Conveniently, that's on the top, except it's just no 2. So it'll just be half du is x dx. So let's write that. Half integral du over to the bottom would be u squared plus u plus 1. All right, so now how do we integrate this? Can we do partial fraction decomposition as a rational function? It's still not factorable on the bottom, at least to me again, because it looks very close to that, as I was saying. So probably not that. But remember, there's a technique of completing the square when it's like a quadratic. So that can help us get a perfect square, and maybe we can do like a trig sub after that. So let's complete the square for here. I think I did this in some previous problems already, but let's review. When it's a quadratic, the coefficient out in front of the square term needs to be 1, which it is here. Then we take the coefficient in front of the first power term, so that's here, and we complete the square by dividing that term by 2 and squaring it. So it becomes a fourth. Okay, so let's rewrite our integral as du over u squared plus u plus this number here, a fourth. But then, if we just leave it at 1/4, clearly it's not the same as here. So we need to add another 3/4 in order for it to be equal. Okay, so 1/4 plus 3/4 is 1, so it's equal to what we had up there. Okay, so the whole point of completing the square is to get a perfect square. So in the bottom, we get a perfect square now. U plus half squared plus 3/4. Okay, so here we can make another substitution. V is u plus half. dv is just du. Now we can say that our integral is, well, du is just dv. This is just v, so v squared plus 3/4. Okay, does this look familiar? This is just arctangent. So it would be half times 1 over square root 3 over 4. Sorry, let me rewrite that. 1 over square root 3 over 4. Arctangent of v over square root of 3 over 4 plus c. Hopefully that's visible on camera. That's a 3. I'm using a kind of fat pen. Okay, so I'm not going to simplify, but I need to back substitute. A v is u plus 2. What is our u? it's x squared. So we back substitute as, okay, so let me arctan v is u plus 2, u is x squared, so it's x squared plus half over square root of 3 over 4 plus c, and that's my answer I get. You can double check if this is correct for me. I did not, because I'm doing this live, I don't have the answers with me. Okay, next, let me just draw a line here. This one should be fairly simple. Sine to the 5th t, cosine to the 4th t, dt. How do we solve this integral? This is a easy trig integral with sines and cosines. So remember the technique for that? When there's an odd power, we save a factor of it. So it becomes sine to the 4th, cosine to the 4th, sine, and dt. We want to change the sine squared in terms of cosine squared because we want to let u be cosine of t, du would be minus sine t dt, which we have sine t dt over here. So we want to change everything in terms of cosine to make our substitution easy. So sine to the 4th is sine squared squared. Kind of like over here, x to the 4th was x to the squared squared. So what is sine squared in terms of cosine? It's 1 minus cosine squared. So this is sine squared, but we want sine to the 4th, so we square that. So this is sine squared squared, as I was saying. Okay, so cosine to the 4th t, sine t, dt. Now let's make this substitution. So we get 1 minus u squared, squared, u to the 4th, and a minus du. Minus sign comes from here. Okay, so we can expand this out to make it all powers, and then it'll be easy to integrate. So it'll become 1 minus 2u squared plus u to the 4th times another u to the 4th du. So we can say it's u to the 4th minus 2u to the 6th plus u to the 8th, it's the 8th du. Okay, so this is just power rule, minus parentheses u to the 5th over 5 minus 2u to the 7th over 7 plus u to the 9th over 9 plus c. We back substitute u was cosine, so minus cosine to the 5th over 5 minus 2 cosine to the 7th over 7 plus cosine to the 9th over 9 plus c. And that's my answer. Okay, let's move on to 14. We have integral of x cubed over square root of 1 plus x squared dx. How can we solve this? So here I see something squared plus something squared. So a good candidate is trig sub. So if you haven't seen my crash course on trig sub video, I recommend you to watch that. I might do it a little differently than what you learned in class. Okay, so we have a something squared plus something squared. So I know that these two are sides of the triangle, and the square root term is the hypotenuse. So we can put x here and 1 here. Pythagorean theorem would work. X squared plus 1 squared is this guy squared, right? So we want to sum everything here in terms of theta. So we need to get x cubed. Let's get x first. How do we get x from this triangle? That is tangent theta. I was about to say sine. Tangent theta is x over 1. So x is tangent theta. We can get dx because we also need that. Dx is secant squared theta d theta. And then we can sub the square root term also. Which trig function is that? That is secant. Okay. So we can sub everything here in terms of theta. X cubed would be tangent cubed. Okay. Dx is secant squared. The bottom is just secant. Okay, and this is just solving a trig integral now. So this can cancel with 1 power on top. So we get a tangent cubed and 1 power secant left. How do we solve this? Well, I see that, I believe there's a rule for this, but if you've seen my trig integral crash course on tangent and secants, I don't remember those rules. But I can easily see that I can save a factor of tangent, because I can let u be secant theta, du is secant theta, tangent theta, d theta, except I need tangent squared in terms of secant, which is easy, because 1 plus tangent squared theta is secant squared theta. So secant squared theta minus 1 is tangent theta. Everything else is the same. Now we can make our substitution. So let me write it over here now. Secant squared minus 1 is just u squared minus 1. Secant tangent d theta, that's just du. This is very easy to solve now. So this is a third u cubed minus u plus c. Got to back substitute twice though, so let's do u first, which is secant. So a third secant theta, I'm going to write it like this. Secant cubed is secant theta cubed, like that, minus secant theta plus c. And what is secant theta? You can get it from the triangle, which is square root term over 1, or we had it over here also. So a third times square root of 1 plus x squared, that guy cubed, minus square root of 1 plus x squared, plus c. And that's my answer. All right. That's how I did this one. Let's move on to the next one. Integral dx over 1 minus x squared to the 3/2 power. So actually, I can rewrite this as dx over square root of 1 minus x squared to the 3rd power, because it's just this guy to the 1/2 power, which is square roots, and that guy cubed. This is just properties of radicals and exponents. Okay, so I see it's something squared minus something squared, so I can use trig sub. So let me set up my triangle. Okay, this time I have a something squared minus something squared, so by the Pythagorean theorem, I know that this guy must be the hypotenuse, x is one of the sides, and the square root term is the other side. Okay, as always, I'm going to sub everything here in terms of theta. I need dx, so to get that, I need x first. How do we get x in terms of theta? Sine theta is x. So cosine theta, d theta, is dx. And then we need to sub this guy also. That is just cosine theta. Okay, from the triangle. All right, so let's sub everything in. Dx we found was cosine theta, d theta. The square root term was cosine, so it's cosine cubed on the bottom. Okay, so this simplifies to 1 over cosine squared. And that simplifies to 1 over cosine is secant, so it's secant squared. Integral of secant squared, that's just tangent, very easy. Okay, so we need to back substitute theta. So what is tangent of theta? Here, we don't have it in our definitions, so we need to look at it in our triangle. Tangent is x over square root of 1 minus x squared plus c, and that's our answer. Very easy problem, actually. Looks intimidating because of the 3/2 power, but after we did a simple trig sub, it was a very easy integral. Okay, I will do one more problem in this video. We have a definite integral this time. Okay, I see a something squared minus something squared here. So again, I'm thinking we can do trig sub. Okay, there might be an easier way. Maybe you can make a substitution. I don't know. And it might be quicker. But I'm going to do trig sub because I already have this set up over here. This is the exact same term as up here, right? So I have the triangle set up for me already. So I'm going to just directly use from here in the F to save time. Okay, so we're going to worry about limits afterward. It's a definite integral. So we want x squared. What is x? X is sine theta. So it'll be sine squared on top, along with dx, which is cosine theta d theta, the bottom, we have the square root term, which is cosine theta. Limits of integration, we had to change them. When x is 0, we plug into here our definition. Sine theta is 0. That's when theta is 0. Okay, how about square root 2 over 2? Sine theta is square root 2 over 2. That's when theta is pi over 4. Remember, by the way, when we do a trig sub, we restrict the domain to a certain interval. So we don't have, technically it's an infinite number of solutions. If you remember in pre-calculating algebra 2, there's an infinite number of solutions when sine theta is 0, for example. Because it'll be at 0, 2 pi, or even at pi also, 2 pi, 3 pi, and negative pi, negative 2 pi, so on and so forth. There's an infinite number of solutions. So when we do a trig sub, we restrict the domain into a certain interval. So hopefully you remember that. That's getting technical, but if you remember that, great. So that's why we can just write it as from 0 to pi over 4. Okay? All right. So here we can clearly see we can cancel a cosine. So we're left with integral from 0 to pi over 4 sine squared theta, d theta. This we know how to solve. This is the half angle identity we need to use. So half integral from 0 to pi over 4 will be 1 minus cosine 2 theta by d theta. Okay, so this is half times theta minus half sine 2 theta. We evaluate from 0 to pi over 4. So what do we get? Half times pi over 4. We plug in the upper bound first, that's what I'm doing. Minus half times sine, let me just write minus half times, what is sine of pi over 2? Because 2 times pi over 4 is pi over 2. That's just 1. Okay? And then when we plug in 0 for the lower limits, this would be 0. Sine of 0 is also 0. So this is our answer. So that's why we change our limits, because it's just easier to plug in at the end instead of back substituting and then plugging in. Okay, so I'll call it a part here. Please like this video if you found it helpful. Hopefully I went slow enough that you were able to get what you missed if you didn't quite get something. Please subscribe also if you haven't already. Leave a comment if you have any questions. I'll try to get to it if I'm able to see the comments. And please also look out for the next video where I'll continue to solve a few more problems.